So today we're going to take a look at 1.3, meaning chapter 1, section 3 of our textbook. So in section 3, let's blow this up a little bit. It says we're going to look at the Pythagorean theorem and distance formula, and then we're going to introduce trigonometric functions. So the key thing is the Pythagorean theorem is something that we looked at back in algebra. The real thing we want to do today is this. We want to introduce defined trigonometric functions, and then we're going to be using those for the entire class and the rest of the semester. And then if you go on from 121 to pre-calculus, which is 191 at DVC, they will review trigonometric functions. And then if you go on from pre-calculus to calculus, they will be reviewing and using trigonometric functions. So in this class, this thing we're going to look at now and introduce is an enormous topic in mathematics in general and is used across all fields and is used across many, many industries as well. And so I want to have us take note of that and be very careful as we introduce trigonometric functions. And if you guys have any questions through any part of this process, please chime in, because this is basically the most important beginning of a topic for the entire semester. Okay, so having tried to hype up today's importance, let's begin with a quick review of the distance formula that comes from the Pythagorean theorem. And they are showing this review in the context of an angle. So we can see the orange lines that they put the vertex of the angle at the origin of a XY graphing system. And then they're talking about having a point in the XY plane. So it says, let the point XY be a point other than the origin. And then it says on the terminal side of an angle. Well, the better way to think of it is that you have a point and then you create an angle that opens up until the terminal side reaches that point. So let's say I have my coordinate system and I just pick a point up here for XY. So then what you're going to imagine with this point is that you're going to use from the origin out to the right of the x-axis as your sort of initial side of your angle here. And that you're then going to draw a line from the origin that goes up through the point, and that's going to form an angle right in here. And that you swept up to that point in the counterclockwise direction, so that will make it a positive angle. And they're showing that here with this symbol here called a theta. So this angle here would be called theta. And that you can now associate that any point in the XY plane has an angle associated with it that you get by traveling counterclockwise from the x-axis around with a line, the terminal side of the angle, until the angle lands on the point, and then that establishes the angle of that point. So we now have an XY point in a plane, and there's going to be an angle theta associated with any point in the XY plane. Maybe if the point is, you may recall that when you have an XY plane, there's quadrants here. So the upper right corner where X is positive and Y is positive, that's referred to as quadrant 1. The one to the left of that is called quadrant 2. And one of the things you can see in quadrant 2 is that it's above the x-axis, so the y values are positive, but it's to the left of the origin, so the x values are negative. So as a reminder, all points in the first quadrant, both x and y values are positive for all of those points, and this will become important pretty soon. And if we move into quadrant 2, all the x values are negative, but the y values are positive in quadrant 2. If I move below quadrant 2, the bottom left corner of the XY coordinate system, that's referred to as quadrant 3. And all the points down there, both x and y are all negative because it's below the x-axis, making the y values negative, and it's to the left of the y-axis, making the x values negative. And then finally, to finish off, the bottom right corner in the coordinate system is called quadrant 4. And down there, the point values are positive for x and negative for y. So any point in the quadrant system now, I can then map an angle and create an angle out to that point where the terminal side passes through that point. And the reason we can see in these quadrants where the angle would end up is that that helps us use some of those language for angles that we had before. So for example, if in my sketch over here, I end up in quadrant 1 because of where the point is in quadrant 1 with my angle, then that's going to cause my angle to be between 0 and 90 degrees. Because the 90-degree angle is when you have straight up and down compared to the bottom, when you have a right angle. So that means any point in the first quadrant, the angle associated at that point would be an acute angle. Or I could move up to a larger angle by going to something in the second quadrant, like in their diagram. They happen to have the point be in the second quadrant. Well, then I know that angle for that point is going to be between 90 and 180 degrees, an obtuse angle. And if I have a point that's way down in the third quadrant, then I know my angle is going to be more than 180 degrees. And if it's in the fourth quadrant, then I know it's going to be between 270 degrees and 360 degrees. And then if I come back and start to have points again, then I can start back at 0 as well. You can also imagine that if I complete the rotation of the angle, that you could go beyond 360 degrees. We didn't quite get to those discussions last time in the formation of angles, just because time ran out. So the angle that they're showing here, if it were, for example, right in between the x and the y axes in the second quarter, then that angle would be 90 plus 45. That would be 135 degrees. So I'm going to say this is approximately equal to 135 degrees. But I could imagine that that terminal line rotates around one full rotation again and would land right up on the same point. If I went all the way around once after that first time of arriving at the point, I would arrive at the point again. So this angle is equivalent to the angle of 135 degrees plus 360 degrees. So this is the same as 495 degrees. That would be another angle that would land the terminal side right on the point XY. So if we have this point XY, then we can also envision the line segment from the origin up to the point itself and the length of that line segment. And to figure out that length, they've shown you that the length of the base of the triangle formed there would be whatever that x value is, at least an absolute value. It would be negative if it was to the left. And if I square a negative number, it doesn't matter if it was negative or positive. So if I square the value of x and I square the height of the point, the value of y, and I take the square root of that sum as they're showing in this formula here, that's a way that the Pythagorean theorem will tell us the length of the line segment from the origin up to the point, which they've labeled as r in this diagram. So this is all setup. It's a setup drawing on stuff we've done before with points in graphing systems, and now sticking an angle right in the middle of all of that and talking about the angle that's created when you have any point anywhere on the graphing system. So let's pause there because that's a lot to sort of just think and look at and absorb. Can anybody ask a question or offer any comments or make suggestions to help understand this better?
If I could, so the 0 here, we're at the angle. Is that a representation of the angle that's going up to where P is?
So that if you're talking about this thing here, I'm going to circle it extra here, this thing here.
Uh-huh.
So the name of that is called a theta. So that's not meant to be a 0 in any way at all.
Oh.
So when you draw that symbol, which I've drawn up above here, that looks kind of like a 0 with a line through the middle, it's actually a Greek letter. So it's not meant to be a number at any way at all. So I really appreciate your asking the question, because that's a forgetting an easily confusing point, which I forgot to clarify. That's my mistake. So appreciate that question. Thank you so much. Yeah, so this symbol here, that's like an O or a 0 where they draw a line through the middle, that's called theta. And it's actually a letter in the Greek alphabet. And we're going to use other letters in the Greek alphabet, like that is like an alpha, and this is like a gamma, and it just starts to sound like a bunch of sorority or frat houses or something. But these are actually just Greek letters. They're not numbers at all. And the reason it's showing up here is because we have like X and Y as the standard variables we regularly use quickly to represent some unknown number. Well, there are going to be situations where we have an unknown number of an angle. Like, what is the value or the measurement of that angle in degrees? Well, when we have an unknown angle measurement, then we also need some sort of a letter to represent as a variable that unknown angle. But what we choose to do conventionally in math is we use a Greek letter when it's representing an unknown angle. So that way, when we see that, we say, oh, that must be the angle that they're talking about. So if I have an X value, it could be an angle, but oftentimes it's not. And when I have a theta, it doesn't have to be an angle, but it usually is. So that's called a convention. It's like a best practice. And so the theta symbol is the go-to unknown variable for an unknown angle, just like X is the go-to variable for an unknown measurement of some other number, like the height of something or solution to an equation or something like that. Is that a little bit more clear? All right, so this theta symbol in yellow here, they put that there because they are saying there's some angle here and we don't know exactly what it is and we're not going to say what it was. So I just looking at the picture tried to approximate it. But in actuality, I don't know where XY is and I don't know what that theta angle measurement would really be. Other questions, comments, or discussions?
So I just Googled Pythagoras theorem and it gave me this diagram. So basically what I got from it is that basically the formula is not trying to directly measure the lines, the two lines. It's basically drawing a box. And so when you say x squared, it's basically for the two sides of the box. And then based on that calculation, they are able to get the area of the biggest box as I've shared in the chart. So basically, as you've drawn here, the goal is not specifically to measure the two lines, but it's sort of to draw a box behind the lines. And based on that, you can then get the length of the line or the radius, basically.
Yeah, I mean, the Pythagorean theorem does go back to algebra, so I appreciate your sharing the diagram. That might help it make a lot more sense for people. But at this point, we're just using it to get the distance from any point to the origin. And that's called the distance formula. But it is based on the Pythagorean theorem. That's where it comes from, absolutely. So that's a good thing to support that. All right, so with this in place, we're now going to define what trigonometric functions are. And so they just give you a big box and they list them for 6 different trigonometric functions. Honestly, I'm not a fan of this approach. So I'm going to work with this, but we're just going to start by focusing on these first 2 trigonometric functions. And I'm going to try to simplify what they're doing here a little bit and make it a little bit more clear. And then we'll worry about the other ones after that. So first things to take note of when you're looking at a trigonometric function is reminding yourselves what a function is. So a function, in general, any function is an association between 2 groups, usually in math, 2 groups of numbers, where the first group is called the domain, and the second group is called the range. An example of a function that you learned early on is the x squared. And in the x squared function, you plug in some number, like 3, and then the function gives you a formula where it says square the 3, and then the answer that's associated with the 3 is a 9. And so a function goes from one group of values or items called the domain to the range, and I'm going to use the old f of x notation up here for any function. An example would be x squared, which would take 3 to a 9 or something like that. But you associate with the function the idea that there's an input into the function, and that the function does something, and then there's an output to the function. So the first function we can look at is the sine, this S-I-N here, that's pronounced sine, and notice it has a theta next to it. So that's the sine function or the sine theta function. That's like saying the f function or the f of x function. And so looking at this notation here, let's go back up to our little picture here, and I'm going to clean it up a little bit. All right, so if we are imagining that we have some point xy, and that with every point there's some theta that corresponds to that. So when we write sine theta, sine is a function. And the first thing to point out about it is that what you plug into the function, what's in the domain of the function, is angles, because they're using a theta symbol here in the sine function. So if I imagine a sine function having some domain and range, input and output, that over here, the domain are different kinds of angles, like 10 degrees, 15 degrees, 75 degrees, things like that. So then you give the sine an angle, and I'm going to say like, I'm going to say 90 degrees. So I would plug that angle into the sine function, and I might write something like sine of 90 degrees. Just like I would write a 3 was plugged into the x squared function, and I got 3 squared, and then I would evaluate. But instead of having some addition or subtraction or powers or some sort of formula to evaluate to see what the sine function does, we have to look at this picture. And so the simplest way, I think, to describe the sine function, and I'll explain in a second why it's equivalent to what they have here, is I'm going to have us instead assume that the xy point, say that the xy point, is on the unit circle. meaning a circle that's got a radius of 1. So imagine that you have a circle here. And that the radius is equal to 1. So then when I pick an XY point, it's some point on the unit circle in which we know that the R value from the middle of the circle out to the point XY is equal to 1, because this is a unit circle, so it's 1, a radial direction 1, and every direction is 1. So what the sine function does is it draws the angle in the unit circle. So if I say 90 degrees, it's going to go, okay, here's the unit circle, and here's my first side, and 90 degrees would be up there. It's going to draw that angle, theta, and then it's going to look at the point on the unit circle at that angle, theta. And what the sine function is going to give us as an output is the y value of that point. So I'm going to say the y value at whatever the angle was, 90 degrees. So if I look at the unit circle and I circle up 90 degrees, I would be right at the top of the unit circle. What would that point be up there? Well, that point is directly on the y-axis, so it has an x value of 0 and a y value of 1. The y value of that point is 1. That means that sine of 90 degrees is equal to 1. And that the sine theta function, if you plug in 90 degrees, it connects that to a 1. Now notice this one measurement, this is not an angle. This is not in degrees. This is a y value. X and y values are real numbers. They don't have degree measurements associated with them. So the input of a sine function is some sort of an angle, and the output of the sine function is a number, and it's a y value of a number on the unit circle. Questions so far? All right, so what if I gave you a different angle? How could we figure this out? So let's say that we have the angle that's shown here, this theta on our picture. And let's say that instead of my approximating it, let's say we knew that the theta that's being shown here is 135 degrees. So if this is 135 degrees, then this line here is halfway between, or splits right down the middle of quadrant 2. Because we have 90 degrees to get up to here. And if this part here is the part above 90 degrees, then that means that that part there is 45 degrees. So if I'm all the way up at 135 degrees, that means that I'm 45 degrees away from the y-axis. And that means there's another 45 degrees down here to get down to the x-axis. So that means this line is right through the middle of that quadrant. So using that information, I can ask, what would be the sine of 135 degrees? So it's the y value of that point. So in this picture, it's this number. That's what this is equal to. And the question is, how do I figure that out? Well, if I'm on a unit circle then I know that the radial line there is a 1. The diagonal line of my little triangle drawn here is a 1. And the y value is the height of that triangle that's formed there. And the x value is the base of that triangle that's formed there. Well, if this is 45 degrees in the sort of x corner there, and we know we have a right triangle, that means this angle up here is also 45 degrees. And if those two angles are the same, that means the sides opposite them are also the same length. And we'll justify some of these things coming up in the future, but this makes what we referred to in the earlier section as an isosceles triangle, where the two sides are the same length. And so what that does to our equation up here is we know that r is 1, and we know that's equal to x squared plus y squared. But x and y are the exact same length. So the y value and the x value are the same. So I could write this as the square root of y squared plus y squared. And that gives me that 1 is equal to the square root of 2y squared when I combine those y squared terms together. God darn algebra. And now I can solve that for y to figure out how big the y value is of this point. Now, you don't have to go through this process here yourself. They're going to summarize these results, but this is what's going on behind the scenes of this definition here. So if I do that, I could square both sides and I'd get 1 is equal to 2y squared. And then I could divide by 2 on both sides and I'd get 1/2 is equal to y squared. And if I square root both sides, that means y is equal to the square root of 1/2. And you may recall in algebra, if you have a radical and you have a fraction, you want to rationalize the denominator and different stuff like that. So another way to write that exact same answer is the square root of 2 divided by 2. So that was a little process there to show that it's possible. I'm not expecting people to do that themselves at this point. But basically the reality is that if you plug in any angle into a sine function, you could see what point is on the circle at that angle, and you could figure out the y value of that point on the unit circle. And of course, the calculator will do this for you as well. Your calculators, you want to have any kind of a scientific calculator. It has a sine button, it has a cosine button. If you put in 135 degrees onto the calculator and then hit the sine of that, then it's going to give you the decimal equivalent of the square root of 1/2. And you can even test that. You could take the number and square it and see if it gives you 1/2. But the beginning phases to think here is that what is the sine value of an angle? It's the y value of the point on the unit circle at that angle. Questions, comments, discussions about that? All right, so I showed you some calculations of how you could get it, but let's just work with that definition for a second. I'm going to go up here just because we have some blank space I can draw on without erasing the other stuff. So let's say I tell you we've got a unit circle here. And let's say I drew a theta here. And without necessarily drawing it to scale, I told you that the point that this goes through on the unit circle is the point where the x value is 1/2 and the y value is the square root of 3/2. You could confirm that this is a point on the unit circle because you could see that if I square those numbers and add them up, I get 1. If I square 1/2, I get 1/4. If I square the right number, I get 3/4. And if I add those, I get 4/4, which is 1. And the square root of the sum of the squares has to be 1. And that's the case here. So if I have this angle and this point is as described there, then I can ask, what is sine of that angle? And what would the answer be? Anybody want to take a guess? So it seems like some students might be lost here, which is certainly possible. So let me go back here. So I was saying that the way we're going to want to view sine, by definition, is that it is the y value at the angle that you plugged into the sine, the y value of a point on the unit circle. So if I tell you up here that theta goes through that point on the unit circle, and I ask what is sine of theta, then it would really be saying what is the y value of that point on the circle.
Okay, I'm going to take a guess here and say that the y value is the square root of 3 divided by 2.
Yes, sir. Questions about that? So the trouble with points on the unit circle as our definitions for our y values is that they're often not very friendly. They have values like this, where the sum of the squares adds up to 1. So you have square root of 2 over 2, square root of 3 over 2, and we're going to look at some other numbers as well. But the key is that this definition for the sine function then is as simple as we can make it. Well, we talked before, last part, about similar triangles. So what if I take this circle that I sketched here and I make a new circle that's twice as big? So instead of having a radius of 1, it has a radius of 2. And I think about the point there on the circle of radius 2. So this is where the radius is equal to 2. And the other one was where the radius was equal to 1. So if I have the radius of 2, then what would the values up here be for that point at that angle theta? Well, the thing to recognize is that the x and the y values of any point, when you draw them in, they form a triangle, a right triangle. And so when we have 1/2 and square root of 3 over 2 for our first point, 1/2 is the x value down here, and square root of 3 over 2 is the y value over there. And that's why the y value was square root of 3 over 2. So if I then move up to a circle that's twice as big, I have a similar triangle to the one we were just looking at, which is twice as big. That means all the measurements are twice as big, like I was describing in our last session. So to get the sides of the bigger ones, I would multiply the sides of the smaller triangle by 2 because they're twice as big. So now the diagonal has a radius of 2 instead of 1. And the bottom length, which would be the x value of that point, instead of being 1/2, would be 1. And the y value up to that bigger circle up here, instead of having square root of 3 over 2, if I double that, I just get square root of 3. So the y value, if the circle is twice as big, the y value is twice as big as the sine of the angle. So what you can imagine of is that you could, instead of using the unit circle, you could scale up to a larger circle, but then the y value that you would get for your function would be, in this case, twice as big. So if I tried to do sine of theta using the bigger circle, and I said, oh, well, I have a y value of square root of 3, what I'd have to do to then get the correct sine value is divide that y value by how much bigger the circle was, which was 2. And then I'll get the sine of that angle. So this is why they give the definition the way they do. They say that the way you get the sine of the angle is you take the y value of that point and you divide it by the radius that you got up to that point, the radius of the circle if you went to that point. So notice that if you have a unit circle, then r is 1. And if r is 1, this simplifies to what I told you. Sine of theta is just y. So when r equals 1, then sine of theta is just the y value. And what that means is that if you have a unit circle, then sine of theta is just the y value of the point on the unit circle. If you imagine a bigger circle, then you would need to take the y value on that bigger circle and divide by the radius of that bigger circle. And that's how they have their formula here. Now, what is the benefit of thinking about the unit circle and making that r go away because you're going to assume it's a 1? Well, you can think very quickly about like the range of the function. If you imagine that what the sine function does is it looks at the angle and on a unit circle, it gets the y value of the point, well, then you can ask, well, what kind of values is that going to produce? The y value on a circle is the height of the point. So if I have a unit circle, the highest point on the unit circle is up here at the very top. And that point on the y-axis is 0 for x and 1 for y, because you know you're going up 1 because this is a unit circle. The lowest possible y value you can get for any point on the unit circle would be down there at the very bottom somewhere when you're at 0 for x and -1 for y. And all the other points on the unit circle are going to be somewhere in between. So that means that for the sine function, the input values, let's draw it over here, will be angles. You're going to put in thetas in here, and it could be any theta measurement that you want. You're going to take the sine of theta. You're going to look up the y value at that angle on the unit circle, and that you're always going to get a number that's between -1 and 1. So as we move forward and you start to warm up to the idea of what this sine function is, if you recognize it as the y value of the point on a unit circle, then you'll know, well, the biggest that ever gets is 1, and the lowest that ever gets is -1. And it could be any number in between those, just depending on which angle I was at. But for example, if you ever are supposed to find sine of some angle, and you had some formulas or you did some work, and then you say, oh, looks like I got 7. Then you immediately know something's wrong. because sine of an angle can never be a number bigger than 1 or less than -1, because the y value of any point on the unit circle can never be higher than 1 or below -1. All points on the unit circle are only 1 away from the origin, and that's the most you can ever get. So a sine is a function. You plug in an angle, like some number of degrees, and it spits out a number. And that number will always be in some number between -1 and 1. And specifically, I could find what that number is if I could go on a unit circle at that angle and see where the point is. Then the y value of that point, that's what the sine value is telling me. Questions, comments, discussion? So if we have a bigger circle, like just to follow along with the example we have above, let's say we have a circle and the radius of my circle is 5. Well, I know one of the points that would be on that circle, just to use nice numbers, would be one where the x value is 3 and the y value is 4. And I know that because by the Pythagorean theorem, 3 squared plus 4 squared equals 5 squared. 9 plus 16 is 25. So there's a point on the circle of radius 5 where x is 3 and y is 4. And I also know that there's an angle from the x-axis up to that point. So we could ask, well, what is sine of that angle? That's some angle. What would be the sine of the angle where the angle is formed when we go up to the point 3, 4 on the circle of radius 5? And we could say, well, the sine is going to give me the value of the point on the unit circle that's much smaller. But this is a similar triangle to that. And therefore, ratios of corresponding sides are equivalent. That's what we saw in our earlier section when we looked at similar triangles. And so that's why we can use this definition down here. I can take the y value that I would have gotten from this much bigger circle and divide it by how much bigger the circle is. So in this case, that would mean that on this bigger circle, the sine of that angle is going to be the y value of the point, which is 4, divided by the radial length of that circle, which is 5. Y over r. Notice that value is between -1 and 1. It's less than 1. So that's a valid value. A sine of an angle can get a value like that. And so whatever that angle is in there, that would be the sine value for that angle. Questions about that? All right, so that's a lot to think of. That's a lot to think about. But we want to start with the definition very, very carefully. It's very important, I think, with the definition to try to think about what it is. What does this sine function do? Instead of trying to think about a formula to calculate. There's a big tendency for students when they first get here to just say, yeah, just tell me what to do, and I'll just do what you said to do. But then as we move forward in the class, students get just more and more confused because they don't understand the purpose of what they're doing or how it works or what's going on graphically or anything like that. All right, so now let's take a look right beside this at the cosine function. That's another function, and it has a domain and a range. You plug things into it, it gives you an answer. And as we can see from the notation, we are still plugging in an angle. So the domain is some sort of an angle, and then it outputs a number. And if we look at what the sine function did, it took a y value of a point and divided by the radial length to that point. The cosine takes the x value and divides by the radial length to the xy point. And if the radial length was 1, if we were on the unit circle, then this definition of cosine would simply be that cosine of the angle is the x value of the point. So when you have a unit circle and an angle to a point, the y value of that point is sine of that angle, and the x value of that point is the cosine of that angle. And one of the ways you can write that is you can say, all right, if I have a unit circle, and I have some point on the unit circle and a theta that goes to that point, then the coordinates of that point are cosine theta, sine theta. Because that's x and that's y. And if I have a bigger circle, where maybe the radius is 10, and I have a theta, and I have a point on that circle of radius 10, then the coordinates of that point are 10 times cosine theta and 10 times sine theta, because it's 10 times bigger, and these are going to be similar triangles with the same angles. And the one on the left, which, you know, I drew it smaller, of course. The one on the left is 10 times bigger than the one on the right. And so the coordinates of that point will be 10 times what was the x value of the unit circle and 10 times what was the y value. And you can see over here, I could get on any point on a circle, I could just multiply both sides of this by r. And you'll see that means that the y value of the point is whatever the radial length is times the sine of the angle. And I could do the same thing for the cosine. Few minutes left. So usually what people start to do to warm up to these functions, since right now it's a bunch of symbols, it's a bunch of theories, there's graphs shown to try to justify things. We've just started looking at graphs at angles, and now we're imagining triangles and angles and radial lengths and all of these things. Is like when you first learned how to do x squared. When you first learned exponents, the way you warmed up to it is you just squared stuff so that you had numbers that you can work with. And so there's two ways that I recommend people start to warm up to the idea that the sine and the cosine functions are a function where you input an angle and you get a number. One way is to just see some commonly used values in a table to just get a sense of it. And the other way is to start typing it in on your calculator and seeing that it makes sense, that it's coming out the way that it does if you can. So for example, if I plug in an angle on my calculator that's in the third quadrant, bigger than 180 degrees, like maybe over here somewhere, there's an angle that's 200 degrees. Well, what do I know about what the sine of that angle should be? Well, at least I could say that the y value over in that quadrant is below the x-axis, so it should come out negative. And if I plug in sine of 200 degrees, you'll get some little negative number that's between -1 and +1. And the kind of table, they have it somewhere, but I'm not sure where because they go about this slightly different way. They basically do what I did with the 6 circle. They go through and have you just use those little definitions. Here's a nice big blank space. Let's finish with this. Let's say I consider some different angles. And I imagine what is sine of that angle and what is cosine of that angle. And again, I would be doing this by just saying, what is the x or y value of that angle on a unit circle? And there are some common angles that are typically used. Like first, nice big whole ones. Like what if we had 0 degrees? 0 degrees means the terminal side did not open up counterclockwise away from the initial side at all. So where is 0 degrees if I'm opening up an angle? It just stayed right here on the x-axis. It didn't lift up at all, and the point would be right there. So if this is the unit circle, and I'm at this point that's immediately to the right of the center of the unit circle, what are the coordinates of this point? What do you guys think? If this is a unit circle, so the radius is 1, what are the coordinates of that point there?
1, 0.
1 for x and 0 for y, right? Well, the sine of 0 degrees then is that y value, which is 0. The cosine of 0 degrees is that x value, which is 1. So we just now evaluated the sine and the cosine at 0 by our understanding of that definition. But we can also start to remember this. So from here forward, forevermore, sine of 0 is 0 and cosine of 0 is 1. That's going to be a common angle that comes up. Now let's go up to another nice one. What if I go up 90 degrees? If I go up 90 degrees and I'm pointing straight up this way, then my point, as I mentioned before, is right at the top of the circle. Those coordinates are now 1 for x, 0 for x and 1 for y. So if I'm at 90 degrees, the sine of 90 degrees is going to be that y value of 1, and the cosine is going to be the x value, which is now 0. Those have switched places. Let's say I go halfway around the circle and I have a straight line. So my angle is a straight line angle. That would be 180 degrees. Then I'm at this point over here on the unit circle. Well, now I've moved over to the left. So x is now over at -1, and I'm right on the x-axis, so y is 0. So what is sine of 180 degrees? The y value is 0. What is cosine of 180 degrees? The x value, which is now -1. And you can see we're hitting our extremes for each function. Each function produces answers between -1 and +1. And this is how we hit those extremes. If I swing down an additional 90 degrees, I end up with a total angle of 270 degrees, 180 plus 90. So when I'm at 270 degrees, the point down here would be now where x is 0 and y is -1. So the sine is the y value of -1 and the x value is 0. And then if I go over to 360 degrees, well, then I'm all the way back to where the 0 is, and the 0 values will just repeat again because I've done one full complete circle.